this talk is about the QuNetSim. This is our simulation platform from TUM. We've been working on it since last year, or a little bit earlier than last year. Yeah, so I'll explain in this talk a little bit about it. So just quick overview of what is a quantum network in the framework of QuNetSim. So a quantum network in QuNetSim is a collection of nodes, and these nodes are connected over a network so that they can transmit quantum states between themselves. And this quantum network is essentially enabling another feature that a quantum network has to do, in our opinion, is enable the ability to share entanglement between distant nodes. So I make this little picture very high level because it's QuNetSim is a high level simulator. So we have Alice who puts her qubit into this quantum network. And the job of the quantum network is to make sure that this qubit arrives at Bob, and it could be routed through some nodes in between. Okay, so I just keep it high level. And that's what QuNetSim thinks of a quantum network. So then the question is, what is QuNetSim? So QuNetSim is a Python framework for developing simulations of quantum networks that have both classical and quantum connections. So it's not a purely quantum connection or quantum network, but it also has the ability to transmit classical information between the nodes. And what does it do at a high level is it's allowing users to develop and test protocols for quantum networks in a high level type of prototypical phase. And so some examples of things that can be done in QuNetSim is writing quantum key distribution protocols. You can simulate quantum money. You can simulate non-risk transmission protocols. So we have some of these examples implemented. Another part of QuNetSim is we could test things like eavesdropping in channels. So if I transmit a qubit between two nodes A and B, and it has to go through a third node C, then we can program the node C to eavesdrop on the qubits and manipulate them en route. So this is something that can be done quite simply. It also provides a toolbox of common quantum networking tasks. So this allows the users of QuNetSim to program their protocols more easily without thinking about rebuilding things that other people have done or protocols that are used all the time. They don't need to write this from scratch every time. So some examples are qubit teleportation, super dense coding, and GHZ state generation. So these things can be done, for example, with one line of code. We use multi-threading behind the scenes. So this is done so that we can mimic the idle times in networks. So for example, if a qubit is transmitted from A to B, B can expect this to arrive, and it's kind of a real-time waiting for this thing to arrive. So we mimic this by using some multi-threading. And so we can also, on top of that, you can also program things to happen during idle times. So this is also a feature of a real-time simulator. So the components of QuNetSim are the hosts. The first one is the host. And these hosts are the nodes of the network. And they have the ability to process and store quantum and classical information. So they can store qubits in a memory, and they can recover them, and they can perform quantum operations on them. And they can also send classical information between themselves. And they have the ability to, I think there's a question. I'm not sure. Interrupt me if there's any questions. They can act as an end node or relaying node. So an end node is the one running the application. They receive and they store the information, they can manipulate it, etc. Like I said. And there's the relaying nodes, and the relaying nodes are the ones who sit in the middle of the network, and they just forward the information onward, but they have the ability to be programmed as an eavesdropper, and they can run any kind of custom instructions. So essentially you write your Python function, you tell the node to run that function, and then it executes. The next layer of QuNetSim is this transport layer. So QuNetSim is kind of packet-based, where we kind of encapsulate all this transmissions into packets. And this transport layer is essentially just there to encode the classical and quantum information and packetize it and add the header information to the packets. But on top of that it's also verifying that things that need entanglement, for example, teleportation, have entanglement. So the user doesn't have to ensure that entanglement exists before saying teleport a qubit. They just say teleport qubit, and then the transport layer will ensure that the EPR pair between the end node that it's trying to send it the qubit to has an entangled pair with it as well. So this kind of the overall vision, as you can kind of see, is keep things simple. And the next is the network layer. And the network layer is performing the routing in the quantum network. So this is something nice, is you can program it to use any routing algorithm you want. It, by default, is your shortest path algorithm, but you can do things based on the state of the network. So maybe there's two ways to get from point A to point B, and the user can decide what is the better way. Maybe they don't want to take the shortest path, or maybe they want to take a path that's longer, but some property of the network dictates that that's a better path. So users can program such things into their simulations. And it can be programmed to drop packets. It can be programmed to apply errors to the qubits en route. It's a kind of a high-level error simulation, but it's something to think about. And it also can be programmed to do multi-hop entanglement. So if we want to enforce if you want to enforce entanglement swapping, then you can just toggle this on the network, and then every entanglement generation that is between 3 nodes will have an entanglement swap procedure executed. Or for efficiency, this can be turned off, and I think it was even mentioned in the previous talk that, yeah, this is established, but it's just kind of established in an optimal or a more efficient way than doing entanglement swapping, but still encapsulates the properties. Okay, so how does QuNetSim work? QuNetSim is a Python library, so it's using a lot of Python threading. So these hosts are kind of all running in their own thread, and they're sitting idle waiting for these packets to arrive. And the packets contain the instructions of what to do with the qubits as they arrive. So this is kind of processed in this transport layer before the application layer gets to see the qubits. So these hosts just run idle, and the packets come, and it triggers an action. And the network is also in a thread. So the network is also expecting network layer packets and stuff like this. And it's kind of similar. So it's always waiting for things to arrive into a queue, and then things happen in QuNetSim. So this is as much of an animation as I can do with my skill, is the nodes are sitting there waiting idle, and they're just asking, is there a packet? Did the packet arrive? Did the packet arrive? Did the packet arrive? And in this time, there's no, and then finally packet arrives, and now the host can do something, or the network can do something. The way QuNetSim simulates quantum physics is it uses pre-existing qubit simulators. So we don't incorporate a quantum simulation directly into QuNetSim, but we build on top of other quantum simulators. So we call these backends. And what we do is we just kind of wrap these backends in our own methods, so that we can make use of their pros and make our simulations more efficient. So we've incorporated 4 backends so far. The first is Project Q. The Project Q is built on like C++ or C even. I can't remember, but it's very fast. So one thing that we do with Project Q is if we want to do things maybe once but really fast, we can use it more to simulate more efficiently. CQC, Simulacron, and EQSN work best with things that are happening for longer durations. And then QTIP is also something new that we've just added into it, and we're finding it works really well in all 3 cases, actually. So, and we left it open-ended. So if there's another type of backend that's really powerful, or something that's missing, users of QuNetSim can generate their own backend and just plug it into QuNetSim, and they can use it just by kind of implementing a few methods in the backend object. So the pros and cons of QuNetSim. So I think QuNetSim itself we're kind of looking at an opposite problem. Well, maybe not opposite, but we're not looking at the scaling problem. I think scaling is a hard problem, and QuNetSim's goal is to be easy to use. And I think as soon as you start going into scaling, I'm not sure, I could be wrong, but I think scaling is a hard problem, and it might complicate the make things more complicated, maybe for us the most. But the goal for QuNetSim is to make it easy for people to use so that they can quickly write prototypes of protocols just to see that does this work. And we saw the talks previously of the stages of research, or the stages of developing something for applications. And in this research phase, I think this QuNetSim is kind of this research phase tool. So the pros of QuNetSim is it's high level. It's easy for people to just install and get started. You can test routing algorithms, so this is kind of nice. It's easy to do as well. You just have to write one function and plug it in. It's easy to debug, so we have lots of logging messages. You see every step of the way what's happening in the network. So if something's going wrong, you can tell more easily. Yeah, it's available on PyPy, so you just have to install it with pip. And we're actively developing it. So every time we go on GitHub and someone requests the feature, we're in contact with them within hours. So I'm really active on monitoring requests and bugs and things like this. So if there's things like that. So the bad things, it's a little, because of the high level nature of QuNetSim, maybe the physical models are lacking. Maybe it's not a good simulator for doing like large scale or kind of repetitive thousands of repetitions of simulations, especially on using physical models. And it assumes a packet-based quantum internet. So this is something that is an open question. I think others would have a better opinion about this, but I think that for me, a packet-based quantum internet it kind of makes sense. I mean, I think you need header information when transmitting something in the network. So I think, but some might disagree with the way it's implemented in QuNetSim. So one would have to take a risk by implementing the protocols in QuNetSim, because that would assume that the future quantum internet is packet-based. The question is, who should use QuNetSim then? So beginners, I think, definitely should be using QuNetSim. People who are just getting into the field of quantum networks, and especially students. So for example, in the last couple of semesters, we've been giving a quantum networking lecture, and we use QuNetSim as an instruction tool. So the students can implement the protocols we introduce, like teleportation, superdense coding, and quantum key distribution. And I think this allows the students to have a better feel for what's happening, and they understand the protocols better when they actually get to implement them, rather than kind of just pen and paper methods. Instructors can use this. I mean, these kind of go hand in hand. They can use them to give projects to the students. For example, one student last semester used it to write his master thesis. He implemented a feature in QuNetSim for distributing W states in the network. So this is kind of something that students can use and instructors can use to develop master thesis projects or so. And researchers, I think, can use this as the initial stage of their research. So I mean, developing protocols you see in papers, it's kind of these noiseless settings. Does it work? And how does it work? And then, if I want to test these things, are they robust? So for example, if I was the first one to come up with quantum key distribution, maybe I would have used QuNetSim and see, okay, now I can use in the noiseless setting, I'm able to run a protocol that distributes a quantum key. So I can verify that these protocols work as an initial stage, and then potentially using other simulators like NetSquid and QuISP to see the robustness of it in terms of scalability and physical properties. So I just want to show a quick example. I hope I have time. Yeah, I do. So this is how we want to implement teleportation in QuNetSim. So the general process is you define a receiver protocol and a sender protocol. So the sender protocol here is, all they do is they generate a qubit, they excite the qubit, they apply the X operation on it, and then you see with one line of code, I just say, send the teleportation to the receiver specified. And then on the receiver side, the receiver is waiting for the qubit, they wait for some time, and they expect it to arrive from a sender, and then they have the qubit, and then they can do what they want with the qubit. So in this case, it's a measurement, and it just outputs the measurement. Then the next stage is generating the topology. Maybe one wants to do this first even. But what we do is we can initialize the network, and then we start the network listening. So this is like launches the threading part. And then we define our hosts of the network. So we have A, B, and C, Alice, Bob, and Eve. Then we define the connections, start them listening, and then add them to the network, and the network will build a topology. And now we can run the protocols. So we just tell the QuNetSim, or tell the host to start running the particular function with the particular receiver. And then it launches 2 threads, and we just wait for them to finish. And then the simulation is done. So the output looks something like this. So you see Alice, Bob, Eve are processing. Alice teleports to Eve. They don't have an EPR pair, so one is being generated. Then the EPR is generated, and the protocol comes to an end. So these are the built-in features. Maybe I'll speed up a little bit. We have the ability to run these with one line of code, send teleports, and super dense, send an EPR pair, generate a GHG set, a state, and generate a W state. So here's it's open source, so here's documentation and the GitHub repository. And the future developments of QuNetSim are trying to generate more of an open source community. So NS3, for example, is a classical network simulator that has hundreds of contributors, and there's really a big community involved in that. And I think something like that for quantum network simulation would be really interesting. Maybe having a graphical interface so that it's easier for people to build the networks. Maybe some kind of drag and drop interface would be helpful. And improve realism performance. I think this is the goal of every software or simulator. And yeah, so, and also building quantum network based applications on top of QuNetSim. So one thing I think could be interesting is if we can use QuNetSim, we write our software, and this can actually control physical hardware automatically so kind of using Python to control physical hardware. I think that would be really nice. I guess it's not so easy in practice. And maybe something like distributed quantum simulation. So I just want to kind of deviate slightly from this and explain a project that's going on. Part of the Quantum Open Source Foundation, they offer a mentorship program. And in this mentorship program, for example, I'm mentoring a student who's interested in working on quantum projects. So in the last iteration, we worked on this project called Interlink. So what Interlink is, it's a distributed quantum computing simulator at small scale. So what it does is it connects quantum devices using connections like this. And what it does is it takes circuits, distributes them onto these quantum processors, and then executes the instructions based on some schedule that's being created in Interlink. So that's kind of just something like that. So we're able to run distributed quantum algorithms using QuNetSim as the communication method. So we can move the qubits around, and generate the entanglement between the processors and stuff like that. So yeah, we've been working on that. Yeah, and it's based on this paper here. Yeah, and Rhea Parekh is the person who did most of the work on that project. I'll just skip this slide. I think I'm out of time. Yeah, so I just say thanks everyone. We worked on this with Janis Nutzel, Benjamin Zenga, and Mert Besse. We developed the QuNetSim over this time.
Thank you, Stephen, for the talk. Now I'll ask the general questions. What will be the first use case for entanglement-assisted communication networks?
Maybe, I don't know. I think I'm not the most experienced to answer this question, but in my opinion, I foresee something like, I mean, a lot of these projects I see are long-distance movement of qubits or long-distance quantum key distribution. But I was thinking about what about like on the short-term scale, like what I mean, literally short distances. What if there's ways to accelerate moving data from one place to another, but within a building or something like this? So what about if we use entanglement for moving data in data centers or something like this, using kind of a dense coding approach? So that's something, the first thing I think of when I think of the entanglement-assisted communication networks. And also, I think I'm on the side of Rodney with the distributed computing. I think this is something that's again in this short. You can use these things in the short length domain. I don't know what the word for that would be. And maybe this is easier to implement because you don't need to consider so much about the fiber loss as much as in the long distance regime. Yeah.
Okay, and the challenges on the path for realization?
Yeah, I guess, as we saw, the hardware development is the hardest part. As a theorist, I don't need to worry about those things. So in my perspective, I don't fully appreciate the hardness of it, but I'm sure I can't claim how hard it is or how easy it is, but I'm sure it's extremely difficult in that domain. From my perspective, the hardest part is just really thinking about what is practical and what is doable, and what can you do with quantum networks. So the hardest part is really come up with the idea, right? The killer app, like we heard. What is that killer app, and why should people convert to it? I think this, for me, in my perspective, is the hardest thing. Yeah.